So what can we do with recursion? That's the question, right? When you're studying the quadratic formula, the question you always ask your teacher is, this is, okay, what am I going to do with this? Well, there are some really good use cases, but the best use cases for recursion are what we call tree traversals. And we call this a tree, even though it's a nested list, we call it a tree because the way the computer sees that structure is a little bit more like this. And you can sort of see, I'm going to regret doing this, you can sort of see the tree structure that we're talking about. I mean, it's upside down, but tree traversal is a complicated problem because a tree can be a very complex data structure. This seems complex maybe at first, but the reality is this is a simple tree. It's only got 3 levels. It's got like 6, 9. So it's got like 10 items in it, 10 nodes or leaves as they would call them. So each one of these names is a leaf node. But what if I tell you that you need to write a function that can count the nodes of a tree? But the catch is this: you don't know how many nodes there are, but you also don't know how many levels of nesting there are. If I tell you it's going to have 3 levels, you could just write separate functions for each one of these, and you could just execute them in order, and you would be able to traverse that tree. But if the tree could either have 3 or 3,000 levels of nesting, there's no real way to do that except through a recursive function. So when we talk about something like this, what we're looking at is how do we figure out how to traverse that tree and count the nodes? If I use a recursive function, then the way it traverses that list, and this is the same thing, just looks a little different. But if I start at the top at 0 on that first list, item 0, index 0, I'm going to have Adam. Index 1 is a list. If it's a list, I'm going to go into that list. So I go to Bob. Item 2 over here is a list. So I'm going to go into that list. I'm going to go Chet, Cat. Then I'm going to, remember, put the top half of that doll back on, come back up to Barb, Bert, all the way up to Alex, because I'm putting the top half of that doll back on. I'm coming over to this one. It's another sublist, B, Bill, and then finally back up to Ann. Why does it do it that way? Because using that algorithm of if it's a leaf, count it. If it's a branch, traverse it. I could have hundreds of levels here with really complex structures, and it's just going to be able to follow them. It will keep following them down until it hits the end, and then it'll come back up and keep going. So what does that look like in code? It's not as complicated as it looks. Okay, the base case is when there's nothing left to count. So that's what we're working toward. If it's a single item, you count it. So if it's a leaf, you count it if it's a name. If it's a list, then you process it like a list. So writing that in code seems like it could be difficult, but in actuality, it might not be too bad. Let's take a look. Okay, so there's my names, same as they were before. Okay, so let's talk about traversal. Count nodes, and we're going to give it a list of names. Okay, and we are going to go for str item, actually for item in list li names if it is a list, if type item equals string, then we are going to count it. Okay. And then else we are going to count nodes in the item. Okay. And then we're going to return xcount. Have to create it up here. There we go. And so then we are going to write print count nodes li names. Okay. Okay, so here's a little bit more detail on that same one. It's got some text in here that I have it printing out to to tell us what it's doing. So let's take a look at this running. Okay, so this is really interesting to me. Maybe not to you, but to me it is. So this first one, it counts Adam, the count is 1. Then it says, I encountered a sublist. Okay, so that's talking about this item, index number 1 on the main list, encountered sublist. Here it is. There's the list. Counted the leaf item Bob. Count equals 1. Why is count equal to 1 right there? Because we already counted Adam. Why is it not 2? Any thoughts on that? You're right. That's exactly right. Basically, we're talking about variable scope here. It's that whole Vegas principle, because the function inside the function doesn't know what's outside the function, which was the first function. So what we're going to see is the only time it's going to say 2 is when it has 1, 2 nodes in that same list at that same level. So you can see it goes through, and look what it does. So when it hits the bottom where there's no more branches, it returns that number back up to the upper list. So it's going up to, after it counts this and this, it now counts Barb. So we've counted Bob, Chet, Cat, and Barb at this point. It has an awareness of those things. And that's why it's 4. And then after Bert, it's 5. And then it returns that count of 5 back to the main function, because it's returned this, 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 and this. So this part of that has been fully counted at the base level and is coming back up now. So we'll add Adam and then Alex to that, right? So we've got Adam and Alex added, and there's 7. Then it finds another sublist, right? It finds this one that has 2 items in it. So here's an interesting and kind of weird thing, is that it's at 7, but now it's going in, it calls another recursive function for B and Bill. So it counts 1 and 2 again, and then it returns those, counts N, which is the last item in the list, giving us 10. And then it finally returns that item back. So by adding that text to the function, you can get a pretty good view of what's going on there. But I could take this and if I wanted to, if my data structure changes, I can add another level in there, and it's going to be okay because I have a structure that is very flexible now, or I have a program that's very flexible. The reason why I added 3 and it went from 10 to 12, it only added 2 to the total, is because taking the place of these, what used to be 1. So it was a net gain of 2. But I could literally do this for an infinite number of levels. No matter how complex that list is going to get, if it follows that same pattern, my program's just going to deal with it. But notice it's going into the E's way up here. And then you can almost see in the list, every time you have a right-hand bracket, that's sort of like putting the top half of the doll back on. You can see where it returns. Return, return, return. That's those 3 right there. So every time it encounters one of these, it goes down a level. Every time it does this, it returns what it counts. So it's just going through this list like a trooper, even though we're now 5 levels down. So pretty cool stuff. Also pretty abstract, right? I mean, it's really hard to imagine when or where you might use that. And what I'm telling you is you probably won't even think about recursive functions or recursion until your next level computer science class. Then you'll probably have a little bit deeper coverage of it. And when you're going to get into probably some really interesting recursive functions and recursion is when you start to think about AI. Because AI has to be able to understand something recursively because it's processing sometimes natural language or a photograph. You have to be able to traverse that from a global perspective and from a very detailed perspective. So you've got to be able to go from big to small and really understand that data. So that's when a nested list or a recursive function is really useful. In basic software design, I have never ever used recursion. I've never had to. And in fact, almost no situation exists where you absolutely have to use recursion. Okay, there's almost no situation that only recursion will fix. It is a way of doing it that can sometimes be a lot simpler, but there's no real you have to do recursion, that's the only way to do it kind of situation. It is sometimes the best way to do it. And one of the situations that recursion can be very useful for is this one right here. Anytime you see anything that resembles a tree, you might want to think, oh, well, trees, recursion. Those two things are almost always linked. So if you're building a web spidering application and you don't know how many levels down that website is or how big the website is, you can use recursion just the way I showed you, where if it's a link, you follow it. If it's not, then you don't. Or if it's an offsite, you follow it. Or an onsite, you follow it. If it's offsite, you don't. It's the same kind of principle. Anytime you see a tree, you might think about recursion. So if you're working on the web spidering application, you might want to think about how recursion could be applied to that. That would be an extra challenge. You don't have to use recursion to do the web spidering application. You just could. So that might be something to think about. So now